Alright, we are back at AP Review. This is 2010 Form B, BC FR6. So you're given a Maclaurin series for the function f, and it converges to f on the interval of convergence that we're going to be asked to find in part A. When I look at this problem, my first thought, similar to the thought I had on question 5 of this same exam, was, oh wow, it's only 2 parts of the question, which feels like a lot of pressure because you know that each part is probably worth 4 or 5 points, and if you feel like you don't know what you're doing at all, it's a little daunting. So take a deep breath and know that each part being worth 4 or 5 points means that there will be certain parts that are manageable even if you get lost a little bit. Me personally, I prefer to have 3 to 4 parts on a free response because then I know if I start to panic on one part, I can just skip to another part. But here with only 2 parts, you really have to take a deep breath and figure out where to start working. So part A is the most predictable question for a Taylor-Maclaurin series. Find the interval of convergence. So that's going to be the ratio test every single time, right? So for part A, right, part A should be accessible points. It's just about doing the ratio test. So the ratio test is the limit as n approaches infinity of the absolute value of a sub n plus 1, which is going to be this term, but with n plus 1s instead of n, over a sub n, which is just going to be this term exactly as it is. So that's going to be the limit as n approaches infinity of, when I plug in n plus 1s, I'm going to get a negative 1 to the n plus 1, a 2x quantity to the n plus 1, over an n plus 1 minus 1, which would just be an n, divided by this exact term just recopied, right? Negative 1 to the n, 2x quantity to the n, and an n minus 1, right? That's my ratio, right? When I clean things up by flipping stuff over, and I'm going to inch myself this way a little so that I can squeeze one more step in. And I think the more of these you do, the better you get at it, right? These guys all stay on the same floor they're on. So the negative 1 to the n plus 1 stays on the top, the 2x to the n plus 1 stays on the top, and the n will stay on the bottom, right? And then everybody in the bottom fraction flips over. So the negative 1 to the n will end up on the bottom, which is going to go right below the other negative 1. The 2x quantity to the n will go on the bottom, which will go right under the other 2x, right? And the n minus 1 will land on the top directly above the n, right? So if we come back over here now, that's the limit as n approaches infinity. Well, the only n's I'm going to end up with left are this n minus 1 on top of an n, because the negative 1s are going to net to a negative 1 on the top, which isn't going to end up mattering all that much, and the 2x to the n plus 1 divided by a 2x to the n is just going to yield a 2x, right? And that ratio should be less than 1. Well, since these n's have the same degree and a coefficient of 1, as these approach infinity, I'm only looking at the leading coefficients, really, which is going to be 1 over 1. So I end up getting that this whole thing is really just the absolute value of 2x is less than 1. Or the absolute value of x is less than 1/2. So 1/2 is the radius of convergence, right? Absolute value of x is less than r. But we don't want just the radius, we want the interval, which means we have to check the endpoints. Since this is a Maclaurin series, it is centered at 0 and is going 1/2 unit in either direction. So up to positive 1/2 and down to negative 1/2. So I need to check those 2 endpoints to get full credit here. So I'm going to go ahead and check what happens when I plug in x is negative 1/2. So if I look at this and plug in x is negative 1/2, I'm going to get a negative 1 to the n. The negative 1/2 times the 2 will be another negative 1 to the n, all over an n minus 1. Well, that ends up just being a negative 1 to the 2n, right? Well, this is an even number. A negative 1 to an even power is going to come out as a regular 1. So this diverges because this is the harmonic series. You might think, oh, the harmonic series is 1 over n, but notice you're starting at n is 2 here. This is the harmonic series. It starts with 1 over 1, and then 1 over 2, and then 1 over 3, and then 1 over 4. So that diverges. When I plug in x is 1/2, I'm going to get this a negative 1 to the n times a 1 to the n over an n minus 1. Well, that's just going to be a negative 1 to the n, right? Because 1 to the n is just 1. So this is the alternating harmonic series, which converges, right? So again, if you need the justification, this is the harmonic series, which diverges. This is the alternating harmonic series, which converges, right? So my final answer to part A then, if I just squeeze this up here, my answer to A is either parenthesis with a negative 1/2, comma 1/2 bracket, because that's included, or if you like it better, you could have had negative 1/2 is less than x is less than or equal to 1/2, right? That's your interval of convergence, right? Either way you like to write it, whether you like it parenthetically or in traditional inequality notation, either of them are fine. Okay, so that's my part A. I personally like parenthetical notation. If you pick this one, please make sure you're clear about which things are brackets and parentheses. Make your parentheses nice and curvy. Make your brackets nice and brackety, which is not a word, but such is it. Or such is life. All right, cool. So, part B. Show that, sorry, I'm stealing an eraser because this is a lot of math. Okay, so show that, show that y equals f of x. So part B, I'm going to try and give myself a little space here. They want me to show that y equals f of x is a solution to, and I'm going to write this up here because it's kind of messy, x times y prime minus y equals 4x squared over 1 plus 2x. Yikes. All right. And they said specifically for x values in the radius of convergence. They called this R in the problem because they said that this R is the thing you found in part A, which is obviously them just trying not to spoil the answer to part A in part B because that would be silly. All right. Cool. So, awesome. So here's the thing. This is a daunting question, right? Like when you look at it, you're thinking, why would they give me this diff EQ? How is it equal to this rational function? So a couple things. First, we take some deep breaths. We know what the Maclaurin series is for y. We have how to write the Maclaurin series for y. We could also write the Maclaurin series for y prime. So let's start by cleaning up this side and then see if we can find how this turns into a convenient rational function. I have an instant thought about how that's going to work, but I've also been doing calculus problems for a really long time. So I'm going to start by writing out what we should look at when we're looking at the Maclaurin series for y, right? So y, if we make our Maclaurin series for y, I'm going to start plugging in n is 2, right? That was an n up there, right? So when I start plugging in n is 2, I'm going to get a positive 1. I'm going to get a 2x quantity squared, right? And I'm going to get that that's over a 1 because it's 2 minus 1. So I'm going to essentially get that this is a 2x quantity squared, right? And I can clean that up if I want, and we'll talk about it in a sec. When I plug in n is 3, I'm now going to get a negative 1 because the negative 1 cubed. I'm going to get a 2x quantity cubed, right? So 2x quantity cubed over a 2, right? And then my next term would end up being positive again, and it would end up being a 2x quantity to the 4th over a 3, and so on, right? Dot, 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 dot. Cool. If you want to clean this up, you can. That's fine, right? You can make this a 4x squared minus an 8x cubed over 2 plus a 16x to the 4th over 3 plus da da da. That's fine, right? If that helps. I can also write a series for y prime, right? I can write the first couple terms for y prime as well, right? So y prime is going to be the derivative of these terms, right? I could either derive the nth term, or I could just find the pattern by deriving these terms, right? If I derive this, I get an 8x, right? When I derive this guy, I get a minus 24x squared, right? When I derive this guy, I end up getting that it's a 24x squared over 2, my bad, 64x cubed over 3, right, plus da 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 da, right? Now, I need to know what x times this stuff is, right? So x times, so now let's look at what x times y prime would look like, right? Well, that's going to look like an 8x squared minus, and I can make it a 12x if I want. I'm going to leave it as a 24x cubed over 2 for a sec, and we'll talk about that in a sec, plus a 64x to the 4th over 3 plus da 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 da, right? So let's look at what happens if I do this thing minus this thing, right? Let's see what pattern we get when we try to simplify this whole thing. So if I were to do x times y prime minus a y, it seems to me that what I get is the 8x squared minus the 4x squared, right? That would be the first, so I'm doing this thing minus this thing, and notice how they conveniently have the same degrees. They line up. So 8x squared minus 4x squared, and again, if you need to do it term by term, you could say, oh, that's an 8x squared minus a 4x squared, right? Plus, the next term would be this negative 24 halves x cubed minus a negative, so that would be plus 8x cubed they're both over 2, right? And then I could do the same thing with the next term, right? I could say that the next term is plus this 64x to the 4th over 3 minus a 16x to the 4th over 3, right? And I get that this is a lot, plus dot dot dot. So now, let's go back up here for a sec now that we have all that written down. Buy myself a little bit of space. I'm going to try and keep that important information in the corner. So what I now have is that I could write x y prime minus y, if I clean this up a little bit, right, as what seems to be a 4x squared, right? When I combine these together, I get a negative 16 halves. Well, that's a negative 8x cubed, right? Negative 16 halves would be negative 8. And when I combine these guys together, I seem to get a 48 thirds times a y to the fourth, right? 48 thirds is a 16. I didn't mean y to the fourth, I meant x to the fourth, sorry. Plus dot dot dot. Well, here's the thing. I suddenly realized that my instincts were right. I know why they were able to give me a rational function for this. They were able to give me a rational function because the only series that we can comfortably say converges to a specific function is if something is geometric and it converges to a over 1 minus r. Well, sure enough, this thing is geometric. My first term is the 4x squared, which is exactly what I'd expect if it was my a. And if I check what I'm multiplying by, I have to times this by a negative 2x to get to the next term. To get to the next term, I'd times by a negative 2x. Oh, that must mean that my r is negative 2x. So x times y prime minus y must converge to a over 1 minus r in the interval of convergence, which would be a, 4x squared, over 1 minus a negative 2x. Yep, that's a 4x squared over a 1 plus a 2x. So sure enough, this function converges to this rational function for the interval of convergence, which is that negative 1/2 to 1/2, where the 1/2 is included. So I'm going to pull up the solutions guide really quick and see if we managed to check off all the boxes on the stuff they were looking for, because this is a fairly complicated question. So here's what they were looking for in their solutions. They wanted you to write the y Maclaurin series, which we did. They wanted you to write the y prime Maclaurin series, which we did. They wanted you to write the xy prime minus y Maclaurin series, which we did. And they wanted you to spot that it was a geometric series that converged to this thing, which we did. So those are the 4 points. Again, that was a really think outside the box kind of problem, and especially since it only had 2 parts, I think that can be a little bit daunting, but there you have it.